In this example, we're told that we have a fluid contained within a piston cylinder device shown here. So here's the fluid, that's the piston, and it's designed to lift a load of 100 kilograms right there. How high can this load be lifted if 1 amp of current passes through the fluid over a 12-volt potential for 2 minutes? So that's what this is. Imagine like a resistor, and there's 1 amp over 12 volts coming into that. And there's also a shaft that's rotating at 100 RPM with a torque of 1 Newton meters for 1 minute here as well. So this thing is rotating around with a given torque and a given rotational speed, and there's some voltage and amperage here. And we're told to assume that all of the work that goes into the fluid due to the electricity in the shaft goes into raising the load. So as we put some electricity into this and we do some shaft work on this, this will go up. Okay, so let's go ahead and calculate the amount of work that's going into the fluid due to the electricity first, and then we'll do the shaft second. And then what we'll say is that all that work is going into changing the potential energy of that mass. So this is really a statement of the first law of thermodynamics. We haven't really talked about the first law just yet in the lecture, but when we're told that all of the work goes into the fluid due to the electricity and shaft, that all the work that is going into the fluid due to the electricity in the shaft goes into raising the load, is basically just saying we're balancing the work here and the work here into the change in potential energy there. So let's figure out the work due to the electricity first. So that work is going to be equal to the power multiplied by the time. So the power generated by the electricity is going to be the voltage times the amperage. So that's how you get power. And that power is a constant. We're told that this is just a constant 1 amp, constant 12 volts. It's acting over 2 minutes. So we'll call that time delta T, electricity. Okay, so that's the power. And let me just plug in the numbers here. So the voltage is 12 volts. The amperage is 1 amp. The time is 2 minutes, but we should convert that over into seconds. So 1 minute is 60 seconds. Oops, I've got that upside down. 60 seconds is 1 minute. Right, so you see that cancels out, and then when you work out the numbers for that, that will come out to be 1,440 joules. So that's the amount of work that the electricity is doing on our fluid. Let me draw a little sort of control volume here so you can see that that's the electrical work going into the fluid. Let's do the same for the shaft work. Shaft work would be the shaft power multiplied by the time. So the shaft power is going to be the rotational speed of the shaft multiplied by the torque. And then again, multiply that by the time over which that's occurring. So I'll call that delta T shaft. And so the rotational speed is 100 RPM. It's rotations per minute. We need to convert that over to radians per second. So 2 pi radians is 1 rotation, and 1 minute, we just saw a moment ago, is 60 seconds. So there's that. The torque is 1 Newton meter. So there's that. And then the time is 1 minute, and we again need to convert that over to seconds. So that would be times 60 seconds over 1 minute. And when you plug in those numbers, this comes out to be 628 joules. So that's the work done by the shaft. By the way, I can get away with just writing these as voltage times amperage times delta T, or omega times the rotational speed times the torque times delta T, only because the voltage and amperage and rotational speed and torque are constants. If those varied with time, then I would need to do these this calculation as an integral. For example, let's say the amperage varied with time. Then the work due to electricity would have to be the integral of the voltage times amperage times a little bit of time as we integrate from some start time to some final time, right? So, but since we're dealing with constant voltage and amperage, I don't have to do the integral. You could sort of see it as V times A are constant. They could be pulled outside the integral. Then you have integral dt, which is just the delta t. Same sort of thing for the shaft work. Okay, so then the last step is we're told that all of that work goes into, all that work that goes into the fluid goes into raising the load here. So we're raising that load. So we're changing the potential energy of that load, right? So that potential energy, the change in potential energy, is going to be the mass times gravity times the change in height. Okay? Now the mass is, we're told, 100 kilograms. Gravity is 9.81 meters per second squared. And we're trying to solve for delta H. So the change in potential energy is equal to the work done by the electricity plus the work done by the shaft. We can plug those numbers in, so this would be 1440 joules from the electricity, 628 joules due to the shaft. The change in potential energy is this 981 kilogram meter per second squared times delta H, and we can solve for delta H. And that delta H comes out to be 2.11 meters. So just to kind of recap this problem, it's essentially a first law kind of problem. We're relating changes in energy to the work being done on the system, the fluid here. And the work done by electricity is voltage times amperage multiplied by the time. So voltage times amperage would be the power, which we would write as W dot. So this would be like the power by the electricity, and you multiply that by time to get the work. And again, if the voltage or amperage vary with time, then you'd have to do an integral like this. And then down here, the shaft work, the omega t is the shaft power, so it's the rate of work per unit. So it's the work per unit time, or the rate of work. And again, if that varied with time, if the rotational speed or torque varied with time, what we'd have to do is do an integral. So we could take into account the time variation, right? But if omega and t are constant, they can come outside the integral, and it looks like that. And then we said the change in potential energy is mass times gravity times delta H right there. And this is essentially our first law statement. Our total work being done, this is the change in energy. Here it's potential energy, and then you can solve for the change in height. All right, we'll end the example there.